Thanks, Brian. So, to reiterate what Brian was talking about, we are interested in looking for a measure that compares distributions in a scale-free manner. What that means is, irrespective of the scale of the measurement that's being done on the system, for example, earthquakes are measured on a logarithmic scale, the Richter scale, and we might be measuring astronomical distances between planets in astronomical units or microscopic distances. The second point is we actually want to try and measure the true diversity contribution of all or part of a distribution. All right, and just to make sure all of us are on the same page, there's no method that's currently available that allows us to compare all or parts of distributions that are different in scale as well as shape. For example, you may have one distribution that is bimodal, or one distribution that's left skewed, or another one that's right skewed. There's no way that one could actually compare these different kinds of distributions except, for example, comparing the centers or spread. So it will be clear what we are trying to do in a few minutes. But here's the idea we use. We use what is called as the number of equivalent equiprobable types that are required to contain the same amount of information or Shannon entropy as the original distribution. So before we jump into what this exactly means, let's first try and understand what do you mean by diversity. So in this picture on the left, you have, for example, let's assume that the x-axis is some kind of species of animal. All right, you have tigers, you have lions, you have gorillas, you have chimpanzees. So on this left picture, imagine this is a histogram, and the way I've drawn it, each of these species occur with the same amount of frequency. Now the y-axis could be frequency or relative frequency or probability, if you will. Now, since each species occurs in an equiprobable manner, we could actually say that the diversity of this jungle on the left is 4, right? Same thing with the jungle on the right. There's 1, 2, 3, 4, 5, 6, 7, 8 species, each of which occurs with the same amount of frequency or same probability. So we might say that the second forest has a diversity of 8. Now the key point here is not just the 8 species or the 4 species, but rather the fact that they occur with the same relative frequency. In other words, the distribution is uniform. So the diversity of a uniform distribution, for a discrete uniform distribution like this, is clear. It's simply count the number of types or number of species. If it's a different discrete distribution, you would just count the number of discrete values that the x-axis takes, assuming, of course, that they all occur with the same probability. Now, whatever measure of diversity we come up with, it has to have this kind of a multiplicative property. In other words, if the number of species doubles, the measure of diversity should also double. Not only that, we actually would like to have a measure of diversity that gives us a value of 4 for the left distribution and a value of 8 for the right distribution. Okay, so we'll come back to this idea. Now, let's focus on what do we do if the distribution is not uniform. Okay, so if you have distributions that are skewed to the right, skewed to the left, bimodal, any kind of distribution that you can think of, then the question is, how do we talk about diversity in these situations? Well, for example, there's more tigers than lions, and then even fewer gorillas. So then you'll no longer have a uniform distribution. So you cannot count the number of species and report that as diversity, because diversity is not just concerned with the richness or the number of types on the x-axis. It is also concerned with evenness or the probability of occurrence of each types. So if you have distributions that are not uniform, then the question is, how do you measure diversity in these cases? The answer comes from the following simple fact, that we look at, instead of counting the number of species or doing anything with any of these distributions, we look at an equivalent equiprobable distribution which has the same amount of information or Shannon entropy as the original distribution. So that's the key point. We convert the original distribution to an equivalent equiprobable distribution that has the same amount of information or Shannon entropy as the original distribution, and then count the number of types of this equivalent equiprobable distribution, and we say that is the diversity of the original system. So in some sense, one has to convert the original distribution to an equivalent equiprobable distribution, and once you do that, maintaining the same amount of information, then you can count the number of types. Just as an aside, if you don't have a discrete distribution, if you have a continuous distribution, then instead of counting the number of types, the diversity in that case would simply be the length or the support of the random variable on the x-axis. Okay. Why are we interested in equiprobable? Well, I already mentioned the first reason. It's because we are interested in richness, the number of types or number of values that the discrete random variable takes, as well as evenness, which is related to the probability of occurrence. So ideally, perfect diversity means every type occurs with the same equal probability of occurrence. That's one of the reasons why we use equiprobable. The second reason is because it's more mathematical. One can actually show that if the support of the random variable x is finite, then the uniform distribution is among all distributions, the uniform distribution is the single one that has the maximal entropy or maximum value for Shannon entropy. So if the original distribution is not equiprobable, then we ask how many states or types or values of the random variable are required so that we maintain the same amount of Shannon entropy as the original distribution. The answer to that question is exactly what we call as the diversity. So, as it turns out, this diversity itself is not useful when it comes to comparing several distributions. So, what we instead do is we compute the percentage diversity contribution from each portion or part of the distribution. So, if you go back to the equiprobable types, let's look at the bigger jungle here on the right. So we know that the diversity here is 8. Instead of reporting the value 8, we simply convert things to percentages. What is the diversity contribution? And let's imagine each of these is a species of animal: tiger, lion, cheetah, chimpanzee, gorilla, and 3 more. So the first one will contribute 1 over 8, right? Or 12.5%. The first two in a cumulative sense will contribute 2 over 8 or 1/4, 25% of the overall diversity. The first 3 would contribute 3 over 8 and so on and so forth. In fact, you can ask what is the contribution from these 3 or those 2 and so on and so forth. The point is, because we have a uniform distribution, it doesn't really matter which 2 you choose or which 3 you choose. Any 2 of the species will contribute 2/8 in this case. The point is, if you don't have a uniform distribution, then the computation will be different, because each portion of the distribution would have to then be converted to an equivalent equiprobable distribution, and then count the number of types in that and divide by the total diversity to compute the diversity contribution. So that percentage diversity contribution is what we call as case-based entropy. Case-based because we think of each value that occurs in the database as a case, and entropy is used because we are using Shannon entropy to calculate the diversity. So case-based entropy provides a common normalization where it computes the percentage diversity contribution up to a certain point, up to a certain cumulative probability of C. Okay. So imagine you have a general probability distribution like this, a discrete probability set. There are n values that the random variable x takes, and each of those n values, x1, x2, x3, occurs with a probability p1, p2, p3, all the way up to pn. Now, if all of these p's are equal, you have a uniform distribution, and therefore the diversity of this data set is just n. This distribution is just capital N, because there are n types and they all occur equally likely. Now, in general, these probabilities will not be equal, right? They will all add up to 1 though. In that case, we would actually have to compute an equivalent equiprobable distribution and ask ourselves how many types are required in that equivalent distribution that maintains the same amount of information or Shannon entropy as this original database. So for each part of this distribution, we can again ask the same question, namely, if you choose the first 3, P1 plus P2 plus P3, that's the cumulative probability for the first 3 types. Then ask, what is the diversity contribution of the first 3 types? Right? Then we would convert these first 3 types alone, imagine the other types don't exist, into an equivalent equiprobable distribution. Of course, we have to normalize the probabilities so that they add up to 1. And the number of types that the equivalent equiprobable distribution will have, maintaining the same information as this part of the probability table, that will be the diversity of the first 3 types. Now, the percentage diversity contribution would be the diversity of the first 3 types, computed this way, divided by the diversity of the whole database, multiplied by 100. So the formulas are a little bit complicated. Now, just to give you an idea of what is going on, let's go back to the picture that I was showing you with uniform distribution. It turns out, if you were to compute, let's focus on the left picture. There are 4 species of animals. If you were to compute the Shannon entropy of this left distribution, right, it turns out the answer is natural log of 4. Okay. Similarly, since there are 8 species here, it turns out if you compute the Shannon entropy of this left of this right distribution, because it's uniform, one can prove that the Shannon entropy would be natural log of 8. So the Shannon entropy itself does not tell us how many, what's the diversity. It's rather the exponential of the Shannon entropy. So exponential of natural log of 4 for this left distribution will give us the number 4, which is the diversity, true diversity, right? Because there are 4 species. Similarly, exponential of the natural log of 8 gives us the true diversity. So this is the idea, actually. To compute the diversity of an arbitrary distribution like this, say, what we do is we compute the Shannon entropy of this distribution and exponentiate that number to give us the true diversity, and that's the way we do it. If you have a part of a distribution, then we need to compute the Shannon entropy of that part alone, assuming the other parts don't exist. So So we'll have to renormalize the probabilities so they add up to 1 for that part alone, and then exponentiate the Shannon entropy of that part alone to give us the true diversity of that part alone. So that's what these formulas are. So I don't want to go into too much detail. You can read our paper, and I think Brian has linked our papers on his website and on his blog. I do want to show you a hypothetical example where we assume that you have a garden, let's say, and we have several different types of flowers. And so here's the data set. Maybe I'm assuming 4 different kinds of flowers: irises, roses, daffodils, 5 different types actually, lilies and tulips. If we, for example, we can play around with this. I've already programmed this. So if we give them all equal frequencies, then you have a uniform distribution. And so obviously the diversity of this distribution is 5, right? And so each type contributes 1/5. So the diversity contribution of irises is just 1/5. Irises and roses together will be 2/5, 3/5. And so on the x-axis here you have 1/5, 2/5, 3/5, and so on and so forth, all the way up to 1. On the y-axis you have the cumulative probability. Since there are 5 types of flowers, each of them will occur with a probability of 1/5, right? So 0.2, 0.4, 0.6, 0.8, and 1. Right? So the idea is that for a uniform distribution, of course, an important result is that this curve, which we call as the CC versus C curve. On the x-axis, you have the case-based entropy, which is the percentage diversity contribution up to cumulative probability C, and the y-axis, we have the cumulative probability itself. That will turn out to be a straight line, a 45-degree straight line. Y equals x, actually, the equation. Now, if we change the frequencies, let's put more tulips, lesser and lesser of 60, 50, 40, I don't know, 30, 20. Now you have a skewed right distribution and the curve slightly changes. If you have a stronger skew, then it changes even more. If you have a skewed left distribution, it changes the other way. So the idea, so the key point is that both the x-axis as well as the y-axis range from 0 to 1, right? The diversity contribution goes from 0% to 100%, and the cumulative probability goes from 0% to 100%. This is the scale-free aspect of this tool. So if you have a different distribution, which is a species of animals or something else, then you can plot both of those curves on the same picture and then compare the diversity of, if you want, the whole distribution or parts of the distribution as the cumulative probability increases from 0 to 1. Okay, I will link this to Brian's blog as well, so anybody can play around with this. So these formulas that I was trying to show you, that is exactly what, so this formula, hold on, over here that I was trying to show you, these are the ones that I used to program that Excel spreadsheet. Okay. One of the things that I want to mention is the order in which you place these flowers. That is a little bit important. So if you don't have any kind of increasing or decreasing order that makes sense, we will always try and use, if it's a qualitative bar graph kind of a distribution, then try to use like a Pareto order, decreasing in frequency. If it's a numerical variable, then the order is automatically clear, right? Smallest to largest. That's how we plot histograms anyways. Okay, so that's the idea behind computing the case-based entropy. And with that, I will turn it over back to Brian, because he's going to discuss where we have used this case-based entropy with empirical examples.